Hello, audience. Hello, Robert.
Hello, audience. Yeah. Yeah, welcome to Fun with RELUX, episode 33. And today it's about
calculation of the occurrency of calculation, and a little bit we have to discuss a little bit about the kind of calculation we are using in RELUX Desktop.
Yep.
And yes, so we hope it is an interesting theme for you today.
Yeah, it's a bit technical, so we will show you how we calculate the values in our calculation, but overall it's about accuracy. So why are we accurate or why not, and what is an influence of the accuracy that you should keep in mind in doing Gleichen calculations? You should be aware what are the failure levels, what can happen, and how can you be as accurate as possible. And also we will declare how accurate we can calculate with our tools. Yeah, this is the topic today. We have a presentation for today, and a small one, just to show you some aspects of the calculation course. We will not go so deep into RELUX Desktop today. It's more about theory of calculation in a way, and yeah, but it will be enough for the full session episode.
Yes. Yes, and the first thing we have to say, or what we have to remember, we guess most of you know this picture, know this formula, the photometric law of distance. The calculation inside of we have various calculations currently, are mostly based on this rule of calculation, where we will calculate the illuminance in a point by dividing the luminous intensity by the
distance
in square.
In square.
Multiplied with the cosinus of the angle.
So this formula is really, really simple. So it's just the intensity divided by the distance in square. This is our illumination. It's just on a point. So illumination can just happen on point, not in areas. If you have an area and value for an illumination value on an area, then it's the average of points. So it's just available on a point and on a vector, so with a direction. And this cosinus epsilon here in this screen is just about the angle which is outside of the side of the direction of the lumina, and this is quite easy. If the lumina is direct above it, then we have 0 degree, and then we have a 1 for this cosinus epsilon, so this is rare. And if we have a value, then it's just diminished. And if you put from the side the light, then it's
0.
Nothing. Yeah. So this is the vector aspect of the illumination. Quite simple and quite simple calculation in total.
Yes, and we also see in this picture we are working here with measured photometric, with measured LDCs, and the accuracy is at least we could not be more accurate as the measurements are.
Oh, 1 second. So it could be that my microphone does not work, but here it looks okay. That it's working. Okay, so it's maybe I just put the microphone on another side, so maybe this is now better for you. Okay, hope. Okay, so this is the formula where we have the direct part. So this is the calculation method where we calculate the direct part, also indirect, but this is the direct impact of the light on a certain point. And this is quite clear. There is less tolerance in it, and this is if you have variant calculation applications. This direct photo, the direct part of the photometric distance law is almost the same. So if you compare it with other calculation applications like RELUX, you have the same values. There's less interpretation and close to 0 tolerance in this. This method is quite simple, but.
Yes, but so also this photometric law of distance has some problems, and one of the most thing is that it only works when the distance between the calculated point and when we can really say that the light is a point light. And for that reason, the calculated point must be far enough away from my light source that I can use this formula. This is typically 10 times the dimensions of the light source. From that point, we can use this formula. In many cases of calculation, like in indoor lighting or so, this is not realistic. And for that reason, we are using something that we can make a kind of subdivision of the luminaires when the calculation points are very close to the luminaire source, to the light source. Yeah. We will later look a little bit more on this point, go a little bit deeper in this detail. But just here at that point to remember that here is one point when we talk about accuracy in the terms of light calculation.
This is down to the measurement. So the measurement of the luminaires happens in a photogonimeter, and this is down to a point. So the complete light of a luminaire comes out of one tiny infinite small point. Where the light is also measured. It's measured as a point and it's displayed as a point, and we calculate out of it like a point. So this is also to be aware of, and of course in source for failures, because in real life luminaire is not in point source, and it's not always far distance. So it works quite well, the method of measuring the LDC and working with the LDC in calculation applications like ours. With far field. But if you getting close to an object, so if you, for example, have in luminaire closer as a couple of centimeters to a surface, then we go into problems, and we have some toolings to get rid of it a bit, but not in total. Besides this far field measurements, it's also possible to have a near field measurement of luminaires. This means we have not just one point where the complete light of the luminaire is distributed. We have a lot of points on the surface of the luminaire where light is measured, what is emitted. And this means we have a lot of LDCs on the luminaire surface and can work with this. Is called near field photometry, but this near field data is not in usage in all the lighting applications. There's no application where I can do lighting design with this near field data. This near field data are also quite huge. Can be up to some gigabytes in file size, because you have a lot of this measurement data. And for lighting design applications like RELUX, it's just too much information. And you do not gain any better results if you have a distance to the surfaces. So in most of the cases where you have in good distance, it also makes no sense to have a lot of these details. But this ray files, this near field photometrical stuff files are used for the construction of the luminaires. So at manufacturers, they are using this near field data in order to construct the optical parts of the luminaire, to decide about the shape of the covering, about the material of the covering. Lenses, reflectors, these are designed and proven with near field photometrical data. Maybe in future, if you have infinite file size, space, and infinite performance, then it's possible to also jump into the near field lighting design, but at the moment you will not gain any more as just more calculation time, except if you have a real near field application, which is quite seldom in architectural lighting. We have in distance of the luminaire mostly. Okay, enough to this near field stuff.
Okay. Yeah. Okay, this photometric law of distance is the most important formula for our core kernel calculation kernels. Mm-hmm. But we have one, and I will start this before we go deeper into the main course. Mm-hmm. We have one part of the program which is called the RELUX, or zonal cavity or lumen method.
Or LOR, I would say. Yeah. For my.
Yeah, okay.
For me, it's the LOR.
Okay, this is. I'm not so familiar with the English, and we have the German Wirkungsgrad method. Mm-hmm. And you will find this in RELUX Desktop, and you will see on the right, on the result on the right side, on the left side, there is also related average value and the uniformity. But this is not a result of the zonal cavity method. This is a part of a backward, afterward running radiosity calculation methods. Here we have the result, which we really get from the zonal cavity method, which is only including the illuminance as average on the complete surface of our room. So this method is only just working on rectangular rooms, and it will also work in some kind of dimension. It works quite good, not so good. We have a loss of accuracy when the room is extreme small, extreme large, or if we have polygonal rooms, then we will try to reduce them to a rectangular room, and this works more or less good. And for that reason, we will have here more or less bigger difference to the radiosity result.
Yeah, it's like using the energy of a lumina, the photometrical energy, and just provide it in the right directions to the room. And so this is really simple in terms of energy draining to the complete room. We have no uniformity information. We have just the amount of energy which is needed. But this is a good start value for lighting design or for a calculation, just to be aware of the amount of lumina, the amount of luminous flux for the room, in order to reach some illumination levels. So this is something which you can see in online calculators, where the formula behind it is really quite simple. It's, I have to say, more simple as we have seen the distance law. It's even more simple, and it's also not just simple, it's also fast. It's fast and easy to use, but you do not have all the results. You just have the energy proportion, which is amount of lumina or the illumination overall level in this LOR method. And it's quite old, so it's from the times,
it was
before we have the computers. Yeah,
interesting. It was used for lighting designs, for light planning, in all the time before computers come into as a standard on our working places.
Yeah, so this was state of the art in the past. Yeah.
Up to the end of the 80s, middle of the 80s, most of the light calculations will be made manually with this kind of methods and calculation.
Yeah.
Okay, and now we will have a look to we come to our the most important calculation kernel of or calculation methods inside of RELUX Desktop. This is the radiosity. The radiosity calculation.
Do not see the presentation? Oh, the presentation not to see. Okay. Okay. We have to switch on the.
Sorry.
We had all the time a presentation where we go along. So now it's switched on. Sorry. We go back.
We go back and
just shortly to
just to show you. Yeah. So this was the picture of the law of distance, and
I'm sure you have the same image in your mind, but at least we will show you. It's quite simple. You know this formula. It's just about the distance. And this is the screenshot about EasyLux.
You know, of the lumen methods of the calculation there on the right side, where we have this is the radiosity calculation after the zonal cavity calculation, and this only is the result of the zonal cavity calculation. And here we are now at a radiosity calculation and about a radiosity calculation core. And the essential thing here is that we will calculate in the first step of the calculation the direct part from the luminaires to all points in the room. So each calculation point on the room surfaces is representing a patch, which will later in the indirect part used for the reflection of the light. This works only when we have a diffuse reflection on our surfaces. So we estimated this is in this situation.
And perfect diffuse.
We have a perfect diffuse reflection, and only in this situation it works. In the most planning situation, this is good enough. So for many, so just if you have a room which is filled with mirrors, then you will have a problem. But for standard rooms, for standard offices, standard floors, so we have typically more or less diffuse situation.
Yeah. So radiosity is the main calculation core. So if you just hit the pocket calculation button in RELUX, you will end up with a radiosity calculation. And this calculation method is perfect for calculations according in standard. So if you want to have standard values in illuminance, uniformity, and so on, this is the method. This is a good balance between performance and also accuracy and also and visualization either. And this method, as Lars said, is down to no any specular, no any reflectance, so with non-diffuse reflectance like a mirror, and also not any transmission. So no glass, no effects by passing light through material. It's just about surfaces which are perfectly diffusing. But the color is counting, so the reflection degree, so it reflects the light, and this is the issue on radiosity or in light calculation at all, the indirect part. So the direct part is easy and is always the same, but the indirect part depend on how many of this indirect patches you create and how many light comes from one surface to another. You can calculate it infinite, and you can see it here in this wireframe sketch. That we have some automatic size division of the surfaces. You can see it here in the larger triangles and the smaller triangles where we hit a lot of energy to a surface. Then automatically the indirect patches will be smaller. And where not so many energy is going through, these parts will be larger in terms of interacting as indirect part with the room. So the light is going to one of these patches and then present the light back to the room out of these patches, but as perfect diffuse distribution and not as a direct part. So this is the method behind. And in terms of accuracy, this is of course a model of the room. This means we again going for diffuse surfaces and not for any clear glossy surfaces. And the main point in having an accuracy in lighting calculation is about the modeling. So how accurate you can model the scenery. So it's depend dimensions, it's also depend of what is in the room, and of course also the reflection of the walls. So if you do not know the color of the walls or the reflection degree of the wall, then it's really hard to calculate correctly, because this has a big impact depending on the room, depending on how direct, how indirect the light is. The surface of the room has a big impact on the results, especially on uniformity. And here you need to have as best as possible the surface properties in terms of reflectance of the walls, of all the objects in the room. And this is the big difference also between calculation applications. This is the indirect part. And we have in RELUX a lot of options where you can set the indirect part to more accuracies. You can also say, okay, I do not want to have this automate patches on the indirect part. You can say, okay, I want to have it really detailed. I want to have small patches for the indirect part. This makes the calculation more accurate, but also gain you or demand in more performance and demand also in higher calculation times.
Yeah. It is normally will RELUX give you good settings for the calculation. In some extreme situations, for example, when you have a really large scene in your project and you will use very small luminaires with very narrow light distribution, for example. So in this situation, you should take impact and start with a finer calculation grid, or otherwise you will lose too much light in the terms of accuracy.
Also, if you put the luminance close to a wall, then it also makes sense to make a finer indirect grid, which you can set in order to see the distribution on the wall smoothly. Also, false colors are affected, values are affected, so everything is down to the settings. But again, if you just hit the calculation button, you get a good average setting, like we have done it here with this dynamic, putting these tiles for the indirect part dynamically according to energy. This works well, but of course, a higher accuracy is possible by setting. But again, it's really depend on how accurate you can remodel the complete scenery. This is the biggest impact on the accuracy on the calculation results.
Yeah.
And not about the calculation method or roundings in the computer or something. It's really about how detailed you can get everything from outside.
One point then we have, because of this diffuse reflection, we can rotate and walk through the calculated room. This is one of the advantages of this radiosity method.
Mm-hmm.
Against the next point we are talking about, or what we want to present, this is the ray tracing. So this is a second alternative calculation kernel which we have in RELUX, closed since the beginning of RELUX. And with this ray tracing calculation, it is possible also to calculate mirroring transmission materials with transmissions. And here we are using a different kind of calculation methods, where we have there are different kind of ray tracing ways. One is a backward ray tracer and forward ray tracer. One side from the eye or from the observer to the light source, or from the light source to the observer. There are also some mixed calculation kernels, and you will really need this ray tracing calculation if you want to get high quality renderings where you have where you need the necessary of to realistic images renderings, and or if you need to have calculation to simulate complex materials inside of your calculation.
So complex means glass or mirrors and so on. It's ray tracing is something which is used quite often in visualization applications, and ray tracing is also quite established to bring you good images in computer visualization in general. The most of the ray tracers outside are just for visualization. So it's also possible, of course, in RELUX to visualize with the ray tracing core. You can access this by the calculation options. You can enable also ray tracing or disable. It's not by default, it's not switched on. So it's switched off by default, because it took also more time as radiosity to calculate this effects with transmission and reflectance. But the special on the RELUX ray tracing calculation core is that you can also obtain values. We can also obtain values for illuminance via this ray tracing method. This means you can calculate the effect of a mirror with a spot. So the spot goes to a mirror, and from the mirror back to the room, and you can really have false color and values in illumination on this effect of an reflectance or transmission. So this is an USP of RELUX with this ray tracing core. Of course, mostly used in the past doing good visualization. So this diffuse stuff in radiosity is not always looking nice, because you have not any gloss effect, like you can see it here on the screen, or not any transmission. Glass is not available in a way for visualization. And that's why ray tracing is a good part of having good images, but these images are just images. You cannot go into the scenery. It's blocked. It's just an 2D simple image. And there comes another, it's not a calculation core. We have another visualization core connected. This is Enscape, and Enscape is something in between. So Enscape make it possible to go in the scenery. You can walk through the scenery, you can move your camera freely, but you have also this close to ray tracing calculation method with transmission and reflectance, but in a more in a game engine way, that you all just what you visualize is in a way ray traced in real time, but primitive without any values, just to make the look and feel like in real scenery. It's not calculated to the last surface. It's just about to give you a nice impression of the scenery with everything light could offer in terms of reflection and transmission. And quite nice work, but this is something where you need to consider as a user. Okay, what I need from a lighting calculation. If it's values for hitting a standard, then go with the radiosity standard out of the box calculation in RELUX. If you want to have an calculation of reflections or in transmissions through glass or with a mirror or metal or whatever, plus maybe a nice looking picture, then go for the ray tracing. And if you have just want to have visual impression, just to have a nice look of the scenery, then go to the Enscape. Enscape is also really fast, and you do not need to calculate anything in order to use the other code. The cores are in a way independent, so you can go with an calculation in Enscape or visualization Enscape without having ray tracing or radiosity before, and vice versa. You can use ray tracing without radiosity and vice versa. And you can also have all of them. And you have in the output all of them. You can compare ray tracing with radiosity with an Enscape impression, not in values, but with an impression, and can compare the different calculation cores. A lot of options, I know. But this is the best flexibility you can have in lighting design, and choose what you are going to need for. And that's also the reason why you cannot just switch off the ray tracing core with Enscape, because there are values you can calculate. So it will be hard to say, okay, the image quality of Enscape is better, and you have a dynamic rendering in a way, but you not get any values. And in the ray tracing core, you can get values. So this is something where each calculation method has its USP.
Yes.
Yeah, this benefits. Yeah.
Okay, on our last sheet here in this presentation, I will go back to this point which we started in the beginning with the photometric law, photometric distance law, and the limits about the size. And here we will see a little bit the simple way we go to this by luminaire subdivision, and you will see in the left picture. This is made with luminaire subdivision, the calculation, and on the other side, when the calculation is only made as a point light source. So many of these CID programs, AutoCAD, Revit, Vectorworks, and so on, they are now actually able to use also LDC files, but typically they will not make this kind of subdivision in luminaires. Even they will not handle the self-illumination of the geometry by itself correctly. So because you must realize that the geometry which is displaced from one luminaire and the LDC is the same thing. And during the calculation, the geometry of the luminaire itself, where the luminaire is the light is going out, must be ignored, because it is already included in the measurement into the LDC. And for that, we should not take the geometry of a luminaire for itself into account for the calculation of the shadows.
Yes. So this is a method where an larger surface of a light output of a luminaire can be simulated to be not in point. So we can here simulate more in surface of the luminaire. So we divide the main point LDC in multiple parts and put the same LDC on it and reduce the luminous flux so that it fits in total. Works well on linear luminaires, on simple rectangular surfaces, but we have an issue if you have some kind of like in sphere. So if you have in sphere luminaire, this subdivision thing is not working quite well. Also in ring luminaires, this is not nice because we need to put it into single rectangles in a way. And Yeah, so yes. This is an issue, but this is the what we can do with good performance, still with far-field photometrical measurements of the lumina in terms of the near field. So this is a good compromise to have enough in performance, but also good values and good visualization, but not going into a lot of more data of the lumina. Yeah.
Okay, at last we will show you the CEE report, but before we take a look to this, I want to show you
ray tracing in real life.
Ray tracing in real life a little bit to illustrate the difference between this. What we are here seen is a ray tracing picture. It is just a picture, and I have just not a possibility to move this around, but I have the ability because, for example, here this surface is not a surface, it's a
mesh.
It's a mesh, and so we can see, we can look through it, and also we will have the light. You will see here from the spot the light here on the back side of this plate. And when you take a look to the normal radiosity calculation, you will see inside of this calculation it's just a diffuse surface. No light is going through the surface, and we have also this here. For example, here the difference of these places which are in for the ray tracing here made of a transparent material like glass or something like that. Mm-hmm. This just to illustrate a little bit more the difference between these both calculation kernels. Mm-hmm. Now at least we will take a look to to the CEA report. This is related to the CE 171 from 2006. Thank you. And yes, the CE report describes a way to
validate a calculation core. So this is it is in CE standard 171. Which provides us test cases, samples, and LDCs in order to validate in calculation core. Not specific for radiosity, for all kinds of measurements. There are some kind of validation sheet, and we have
a lot of papers, so we cannot,
of course,
everything.
And and here we have an validation report from the Uni Athens from Greek. They has done this test according to the CAE standard with RELUX desktop, and we published this study from the university on our website. So if you go to our website relux.com, there is a section download, and in the download section you can find this validation report according CAE 171. And here you can find in detail the accuracy of the calculation core according to these test cases. So, for example, there are defined photometric LDCs, photometric files, and we have down below we have some test rooms, and in the test rooms you can see how the luminars, the defined LDCs, are located, and then we have some results, of course, on specific points. And here, in short, the red lines is some kind of the border limits below and above for the values, and there's also some kind of a fine grid value, and the green line is the results of RELUX. And you can see here nicely that the green line is in all situations on all the LDCs in each different test rooms always in this tolerance of this band. So this proves that at least according to CIE standard, RELUX desktop is valid and works according to definition of a calculation core. And this report is not just about indoor; it's also about daylight and outdoor, and also transmission of daylight into rooms and so on. There's a lot of test cases. This document is also quite large with a lot of reports. And we cannot go in detail, but again, it's always the same, different scenarios, and we are always in the middle of this. There are also some test reports from other universities out there where students try to evaluate the preciseness of a calculation with RELUX with real-life measurement. Mainly vice versa. So first with the real-life measurement, and then rebuild the measured scene into RELUX, and then compare the results. And there we have results below 10%. So 10% if you have a really accurate rebuilt measured scene, including all the reflection degrees and all the correct LDCs, you are in a tolerance bandwidth of 10%. And this is quite okay for light. So it's not visual at all. And this is also good to keep in mind what you are doing. You have intolerance bandwidth if you model everything really accurately to the real life situation, then you end up still with 10%. So and lumina can vary it. So not any LDC measurement is a sample for all the luminas from the same series. There are also tolerances in creating luminas. There's a tolerance in the power transmission. There's also a degradation of the light source, of the surrounding. There are a lot of influence to the results in terms of temperature, air pressure. There's a lot of influence for a lighting level, and this all in total has an interesting bandwidth. So 10% is just the accuracy of the calculation, and even in the measurement on site, it has also a tolerance in failure. So the measurement tools have a failure level, and so everything which you do on site, the voltage on site has also an impact, and so on. There's a lot of stuff you need to be in the calculation if you calculate something like in failure level. And yeah, and even the measuring has a failure, so the calculation is also in a way bound to this, and there's also a failure. So you cannot precisely hit down a specific level. You have always intolerance, and you have to deal with it as a lighting designer, and need to communicate it. You need to, okay, I have not hit the value there. Keep in mind this is plus minus 10%. In single points, even higher. So it's just the average, which is 10%. So in single points, it could also be up to 40, 50, I don't know, in a distance on a single point. Yeah.
In a worst situation, it may happen that you have, for example, you have luminaires with a less luminous flux than calculated, but the reflections in your rooms are higher than you estimated, and so you have the correct results with two errors or two mistakes inside of your calculation.
Yeah, the average is helping on this. We forgot to mention there's also a smaller calculation core for outdoor lighting, more bound to direct parts, and also one for tunnel.
Yes,
with a bit of indirect parts. Yeah.
Yes, this is the street and tunnel calculation is also related to the photometric law mainly, but includes a special point which is described in the CE 140 for the road calculations, the luminance calculation on roads, where we also not use diffuse reflections. We are using directed reflections related to the R tables, which are
the street surface.
The street surface, which is measured for the typical observer as a driver, is a car driver. And so this is a little bit a variant which we have not presented here at the moment.
Mm-hmm. Good. Okay. Then let's jump into the questions. So if you're interested, please download this document. It's publicly available on our download section. So let's see what kind of questions we get.
So if we have one, yes, we have some.
Can we see?
Sorry.
Yeah, okay. It was from the beginning. The diagram was not to see.
Sorry again for this. This was our mistake.
Okay. Can I ignore a specific point in the calculation result so I will not be considered in the average calculation? For example, a very low point at a corner that influences the average in a distorted effect. Yeah, it's complicated. Yeah, it's also depending on the grid. So
yeah, the thing here in this point is typically that you should reduce a little bit your measuring surfaces. That is what you are also doing in realistic. When your measuring point comes very close to a wall or to an edge, if anybody will make a measurement in such a room, you will not go with your luminance meter totally here, directly here to the wall and try a measurement. It is also gives you in the standards like the 12464, we have typically half a meter from the walls away. So this is the main feature. What we not can do at the moment that when we have a calculation grid on a measuring surface, for example, that we remove one single point from the average calculation. What you can also do is that you don't use measuring surfaces, you use single calculation points. So and there you
can
are free.
them, yeah.
You can improve them. But you must also be a little bit careful when you're talking about average calculation. You must take care that that each calculation point has is representing the same area, so that the average calculation works correctly, so that you can calculate correctly average values.
Yeah. The grid has a high impact. So grid is something where you should really precisely, because the grid has a big impact on especially uniformity, but also in the average, of course. Minimum, maximum is quite sensitive to the grid. There's not so many grid definitions. There's one specific 12464 grid definition, so in standard grid, which is this logarithmic approach about the side scales. And if you stick to this, so if you reference to a standard in terms of min, max, uniformity, average, if you stick to a standard, then you need to obtain this grid 1-to-1, which is defined there, and it's defined. The grid is defined also in the standard. If you put away one grid point, then you're not according the values according to the standard anymore. Then you have your own grid with your own values, but not a reference to the original standard. So this is dangerous to delete single points. Of course, what is more effective is you can try, if it's possible, to reduce the complete size or to skip the complete row, or to change your measuring area, and then you can say, in this area I'm with the standard. In this area I can guarantee, or not guarantee, in this area I have measured what is according to standard. If you extend this area, then not, or you just move the lumina a bit, depending on the scenery. But to change the grid, it's dangerous, because then you not related to the standard anymore. There's also, if you change the amount of points, it's also dangerous. Then you are not also against the standard. This is also an issue if you have if you go to a grid size where you have a lot of grid points in it, which brings you a better smooth visualization of isolux lines or false colors, and brings you overall a better accuracy, because you have more measurement points. This means you are more realistic to the real life. But in real life, this area is not visible, and nobody will measure in centimeter steps the surface anymore. So it's not real life in a way, because you cannot visualize it in real life what happens on the virtual grid, and then you are not according the standard. So this is also something where you are getting over the standard, because you get more points as in the standard, and then you have problems with uniformity potentially, because if you are thinner, you have potentially more dark spots in it or more high spots in it. So it's mainly about uniformity. It was an old tip: if you have problems with uniformity, check first if your grid setting is according to standard, because this is quite rough. And if it's quite rough, then you have better uniformities, potentially, depending also on the luminance. Yeah.
Okay, here one question, very short. Hi, Tore. Yes, good flight back. Yes, you can download the webinar later. It will be available in YouTube and also on our page.
relux.com/fun-with-relux or YouTube. You will find all episodes on YouTube.
Then here, can the calculation grid strictly measure to a rounded distance like 1 meter, 2 meter, etc.? It is always, it is an interesting feature to think about it, but in the consequence, we have to reduce the size of the surface. But however, yeah, I know that sometimes this would be an interesting feature, and so we will think about it. Actually, we have the problem. We have a surface with dimensions, let's say length or width, and we need an odd number, a full number of measuring points on it. We cannot have a half measuring point. This is not possible. So we need a full number of measuring points, and these measuring points must be have a unique distance between the measuring points. Otherwise, the average values are not responsible for this area.
Yeah.
So this is the point. Okay.
Be careful with the grid.
Yeah, be careful with the grid.
Don't mess with the grid.
What tolerance can you expect to be acceptable if you perform road calculation in RELUX versus Dialux or other lighting reality? I guess there should in the road calculation, you will not find really a difference between Dialux, and I don't have not so much experience with lighting reality, but there should at least no difference in the calculation results.
It's just a direct part.
Yes, we have some reasons for the way like the interpolating is done when it's used from the light intensity values from the LDC. There may be a little bit difference in the way the interpolation is done, or also in the handling in general, so that you will say you will not have really on the fifth digit the same result, but in the terms of a normal planning value or something like that, you should have the same results when I'm talking about illuminance or luminance. In some other values, there is something a little bit like there are a little bit more possibilities in the way you have to calculate it, and there may be small differences. But as we know, there are no relevant differences in the light calculation and the road calculation.
Yeah. Where can I have help with the RELUX CAD for Revit software? Yeah, simple answers. We have something like a self-study. So you can go to relux.com. There's a self-study section, and there you can find RELUX CAD for Revit self-study seminars, which takes you 1 day in general to go into RELUX CAD for Revit basics. There's also a course for emergency, especially emergency with RELUX CAD for Revit. If I remember correctly, we have also an advertising running. It covers, I'm sure, the RELUX CAD for Revit emergency self-study for a discount of 50%, if I remember correctly. But the standard RELUX CAD for Revit is charged normally, but it's not a high impact on your pockets. This is quite easy to acquire, not high costs. If it's more needed, we can also arrange real online seminars, real life seminars. This is possible also, but then of course with the fee of a trainer in a way. I can recommend, if you go for RELUX CAD with Revit and you have less or non-experience with Revit, go to a Revit course before. So you need to understand at least the basics of Revit before you go into RELUX CAD for Revit. This is also recommended.
At least this is related to the question before. Multiple calculation areas would be able to share the same grid distance, since they are different in the size, but they would measure the same way. This is the point. It is not possible that you have a correct average value, and this is mainly one of the main quality criteria we have on measuring areas, is the average value, which we have on a room or on a table or something like that. But if you want, you can share me your ideas please send it to support@relux.com, and then we will go a little bit deeper in these details and discuss these points.
And yes, Tore, we explained roughly that the red tracer can also be used for luminance calculations, but we did not show it. I'm not sure, did we had a red tracer episode?
I thought we have somewhere.
Yeah.
Here a little bit today the focus is a little bit more on the accuracy, and for that reason we are discussing a little bit about the different calculation kernels we have inside.
I'm not sure. Maybe we had already an episode which covers the ray tracing and visualizations, and there potentially we have also one measurement quit in it to just demonstrate that you can calculate with it. So time's up. Thanks for your questions. We almost get covered all of them. Next episode will be on the 16th of May with the same time slots. So 10 in German and 14, also 2 o'clock p.m. In English, Central European summertime, for the next topic, which is maintenance factor. So also next episode will be a bit of more technical stuff regarding maintenance factor. Also really important for lighting design to deal with maintenance and maintenance factor. Could really mess up your calculation or really improve your calculation. Good. Sam, see you next time, 16th of May.
Thank you. See you next time.
Bye-bye.